Kim, and I am a master's student in Ewha Women's University, South Korea. And I would introduce myself as a runner. I like running. So, but my lab is more about clinical uses of footwear rather than sports. But I like sports, so I asked my professor to buy this one, and this is how I started my business. Carbon-plated running shoe, as you guys all know, are a high-performance shoe that includes stiff carbon plate embedded in resilient midsole foam. A key factor of carbon-plated running shoe is longitudinal bending stiffness, where higher LBS usually improves the toughness. However, there is a critical trade-off exists. Equal, thicker, and softer midsole improves LBS but can lead to reduced stability, potentially leading to injury in runners. So my research question is it possible to tune the LBS and stability of carbon-plated running shoe by FEA? So I tried to define a FEA model which can investigate the effect of the foam material and carbon plate thickness on LBS and stability. So this is the method how I acquired the geometry for the FEA, and the Nike Vaporfly 3 was employed as a benchmark. Geometry of both midsole foam and carbon plate was 3D scanned, and to enhance the convergence of FEA, midsole geometry is smooth and carbon plate is converted into shell. As you can see in figure B, carbon plate is embedded in midsole foam for further presentation. So this is about material properties. For the midsole foam, I used the first order hyperfoam model, and for carbon plate, I used neo-Hookean hyperelastic model. And I use three materials which is commonly used in running shoes: EVA, TPU, and PVA. And for the carbon plate, I use three thicknesses: 0.75, 1.5, and 3 millimeters. So it resulted in a total of 9 combinations of midsole foam and carbon plate. And it would be better to test the mechanical behavior of the foam and carbon plate, but it was hard for me to make the specimen for this shoe. So I used the reference data. And these are boundary conditions. A total of 2 FEA simulations were conducted. 3-point landing simulation evaluating LBS and ankle sprain simulation assessing the stability. Adaptive dynamic explicit server was used under quasi-static conditions where kinematic and kinetic energy is much smaller than internal energy. Global mass size is decided as 4 millimeters with mesosensitivity test provided in appendix. And 3-point bending was based on the widely used method of evaluating LBS of footwear. And 15 millimeters of vertical displacements download were applied in the center of the forefoot. And for the ankle sprain simulation, motion was simplified by modeling the calcaneus as sphere and making it to move diagonally downward without replicating the full foot model. And this is the results. And I also conducted validation. Validation were conducted by comparing FEA with PEB material and 1.5 thick carbon plate, which is identical with Vaporfly, and mechanical testing. Validation showed good agreement with experiments with about 10% error across most ranges. Slightly higher reaction forces would be likely due to the outsole and the bonding layer, which is not included in the FEA. And these are the results. The colors represent the foam material, and the shape of the line represent the thickness of the carbon plate. As a result, LBS increased with carbon plate thickness increase, but it was less than proportional, suggesting that excessively thick plates are not needed. And EVA showed higher LBS, which is comparable with PVA, while TPU had the lowest. And this is result from ankle sprain simulation. In this graph, higher reaction force suggests greater resistance to this deformation, which indicates better stability. Ankle sprain simulation showed no significant change in reaction force with varying carbon plate thicknesses, which implies the carbon plate thickness is not influences the stability. And EVA and PVA demonstrate higher stability than TPU. My conclusion is I successfully defined the FEA model that can be used to evaluate the FBS and stability with diverse foam materials and carbon plate thicknesses. Through proposed FEA simulation, it would be possible to predict the performance of running shoes before human testing, allowing for efficient narrowing down of running shoe designs. Key finding was that LBS is influenced both by foam material, not only carbon plate. Also, real food stability is largely governed by the foam material with carbon plate having minimal influence. My study has limitations. Firstly, material properties in FEA was from existing literature. So I'm trying to characterize the tensile and compressive material properties from indentation tests. So some students who want to study about the running shoes can just cut the shoe in half and just indent it. And nextly, the proposed simulation does not fully represent the mechanical behavior under actual running condition. So I'm trying to incorporate the full foot FEA model in optimizing running shoe design. So these are the links for the related works in our lab. Thank you for listening to my speech.
Questions from the audience?
Hello, from Info University. When you doing finite element simulation, you use the static or transient or dynamic simulation.
Yes, I use the Abacus dynamic explicit solver, but as it is dynamic, but it was considered as quasi-static status to showing that kinetic energy is much smaller, like 1% of the internal energy. Because I did it because I have to validate it, but using Instron I can hardly simulate the dynamic situation. So for the validation, I use the static.
Yeah, I have two questions. So first question is regarding the, is there any criteria that you select those three specific thickness that included in your simulation? And the second question regarding the, can you share more information about how you set up the dynamic simulation of the ankle sprain scenario?
So for the first question, it was doubled and divided into two. The original thickness of the plate was measured as 1.5 millimeter, so I just doubled and divided into two. And for the second one, you are asking about the boundary conditions, right?
Yeah.
The key boundary condition of ankle sprain simulation is the angle of the displacement and the magnitude of the displacement. For deciding the angle, I searched for the reference, and one reference says that the threshold of the ankle sprain is about 40 degrees, so I selected it. And for the magnitude, I simulated and I assumed that the 80 kilogram man is heel striking. So it was assumed to be a 1,500 Newton, and it showed about 0.3 to 0.2 strain in whole midsole. So it was, the thickness of the shoe was about 43 millimeters, so I multiplied it and I decided the magnitude.
Did you apply to any displacement restriction to the ball while you apply the force to it?
No, it was displaced. The displacement was defined, and the rest of the 5 degree of freedom is restricted.
Time for one short last question.
Thank you for your presentation. Is there any specific reason for not using the ISO standard for the longitudinal bending stiffness of the shoe?
Because you mean why I didn't
The
use
experimental protocol you developed, so it's a 3-point bending test, but then there are some ISO standards so that the study can be standardized across all different studies and we can compare them.
Yes, like,
Since it's an FEA, it can be easily done according to the ISO standard as well.
yes, like, at first I used the standard, but I found that especially for geometry, like modified geometry was better for the FEA simulation because it has to converge. And for the displacement of the jig, I find that 7.5, I thought that 7.5 millimeter of displacement was not sufficient because there was some edge in the missile. And so I can hardly see the deformation of the carbon plate. So for the evaluation of FBS, I thought the 15 millimeters of displacement would be more adequate.
Thank you.
Thank you so much.
Thank you.